You guys, you all know the linear relationship, straight line equation, and in fact there's two parameters that we identify to calculate the equation of the line. The slope means that we can adjust the angle of the line to anything that as required for the relationship, and the intercept here means we can shift the line up and down. So changing the intercept shifts the line up and down, and changing the slope involves the parameter m for the slope or gradient of the line. Now, many physical relationships are actually exponential, and in fact it turns out that there's just two parameters. In fact, an exponential equation is of the form, in the very general form, it would be y equals a to the x is an example of an exponential equation. The most often seen one that's similar to your pH and is base 10, so you know you can use this relationship and the log base 10 to calculate absorbance and pH and so on. However, it turns out that there's a very useful function using the base e, exponentials number. So this actually turns out to be the most versatile form, where e is Euler's number and it equals about 2.8. It's a little bit like pi, it's a mathematical constant. And this one has the unique property that the slope, which is the rate of change at any point in the function, is equal to the magnitude of the function at that point. So in fact, the preferred model is in the form y equals e to the x. 10 to the x works well because we're used to decimal system and powers of 10 and everything. So from that point of view, things like pH, stuff where we're not graphing but we're just calculating a scale, base 10 works well. But in plotting data and describing exponential relationships, it turns out that this Euler's number e is the best base to work with. Now all three of these functions pass through this point here. So this is the point here, 0, 1, like so. And it's easy to verify that if you substitute x equals 0 into any of these expressions, you get y equals 1. It's a property of the exponential equation. So you'd have x on this axis. It will often be, it could be time and you're looking at bacterial growth. It could be distance and you're looking at, well, a negative exponential relationship in the case of light entering water, or your absorbance of light through a solution. In any case, this is our x-axis. Y might be count, it might be absorbance, light intensity, it could be the strength of a particular drug or contaminant in a water body. So, in fact, so many relationships can be modelled. Now, similar to y equals mx, in fact, if I come back to this one, the very general form would be perhaps y equals x, and you just have the line starting at 0 with a slope of 1. And then from there we can change the slope using m, and we can change the intercept using c. Similar here, I can postulate a form of the equation, and note that there are now two parameters that can be adjusted. A, which turns out to be the starting value. So once I get to this form of the equation, you note if you substitute x equals 0 into this expression, y equals a, so I now have a starting value a here. I seem to have used permanent marker again, so that is 0a there. I thought that one worked very well. That's now 0a, just as this is 0c, the intercept in the straight line relationship. A performs exactly the same function in an exponential relationship. And then we've got the value k, which in fact can be positive or negative, which adjusts the rate of change of the function. Okay, so we've got two things: we can adjust the starting value, and we can adjust the exponential rate. Okay, from y equals mx plus c, we often need to work in the form, and in fact with our concentration analysis with the absorbance on the spectrophotometers, as often as not we're going to this form to calculate final concentration on the x-axis here. So the actual application we've been using here is an absorbance here. This could be any number of relationships. Certainly this is not a calibration curve, which would be a linear relationship. This is more natural phenomena that we model here. Similarly here, there's a transposition that can be formed to get the expression in the terms of x. Now the details of that one are in the learning guide. You don't have anything in your workbook related to that. But generally the operation, I can take logs of both sides. Now natural logarithm is to base e. So when I'm working in this base e, we use natural logs as opposed to the normal log function in base 10 if we're dealing with this form of the expression. And this one could also be ae to the 10 kx, for example, for a general form of that one there. Anyway, taking logs of both sides here, we've got natural log of y equals natural log of a e to the kx. And then you need to know your laws of logs to simplify this out. And it's not difficult if you spend a bit of time on it, because it turns out if you take the log of two numbers multiplied together, they actually just add. So that is the same as, it's easy to show that that is exactly the same as that in terms of the rules of working with logs. And this actually equals, this expression here just simplifies to kx because of just the definition of the logarithm. So we end up with an expression like so, and then you've sort of got y equals mx plus c here, and we've got x simplifies here to ln y minus natural log of the starting value over k. Okay, and if this is an exponential relationship, if I was actually to take the natural log of each of these values, so I just work down with my calculator and create a second set of data, which is the natural log of these numbers. Then if I was to plot this pair as an xy pair, you would get a straight line. That's part of the maths that works with the exponential relationship.